Hey friends, welcome to follow up. Let's look at problem 2971. Find polygon with the largest parameter. This is today's daily challenge problem. So this problem actually can be solved by sort and then do a linear scan. But here our purpose is to practice the use of partial sum, and also we want to practice binary search. So here we are given an array of positive integers called nums of length m. So we want to find the largest possible polygon parameter, right? So in other words, the sum of the edges length. So here actually it gives us a condition, right? So the longest side of polygon is smaller than the sum of all the other sides. Or if you have already sorted the array, then we just need to check a1 up to ak-1 is strictly larger than ak, right? Because all the other such equalities will automatically true, because if the right hand side switched with the 1 in the left side, it's automatically true, because the left hand side includes the largest one, right? So essentially we just need to check this one, where ak is the longest edge after we do the sort. So we want to return the largest possible parameter of a polygon whose set can be formed from nums. Otherwise, we return -1. So here, if you look at the examples, let's first look at example 3, because here it has 3 edges, right? But then the longest one is 50. But if you sum all the smaller, shorter ones, you get 10 at most, right? Which is strictly less than 50. Therefore, we cannot form any polygon, in particular trigon, which is a triangle, right? So in the first one, so it actually corresponds to a equilateral triangle or trigon. So just 5 plus 5 is for sure greater than 5. So in the second example, and actually after you do the sort, actually you can see 5 is actually the largest possible one, right? So here, as explained, they have 5 sides. The longest one is 5, right? So notice that if you have 1, 2, 3, which is larger than 5, then you should include all the smaller edges in order to form larger sizes, right? Larger number of sizes. So that's this can be very crucial. So we are going to emphasize this simple, I would say, but not crucial observation for this problem. Here the constraints are the following. First, the number of elements in this list is bounded above by 10 to the power 5. So this basically defines the problem size. And the numbers or the edges length is bounded below by 1. So with that said, we are ready to do the coding. Now, before we do that, let me first point out the trivial yet crucial observation for this problem. So after we do sorting, then for a given longest edge, let's call it A. So if we could find a set of shorter or equal edges with sum whose sum is greater than A, then it means that we can form a polygon, right? Then we shall also form a polygon with all the shorter or equal edges, right? So, but we maintain that the longest one will be just A. The reason is that if you add more short edges, so you even larger than the longest one, right? So if you can digest or grasp this observation, then basically solving this problem is trivial in some sense. So here, let me first do a hard way to do this. So when we see hard way, because I want to practice binary search. So this is actually not absolutely necessary, but it's good to know. So let's first sort this list in place, right? So after we do the sort, I want to find a partial sum. So let's see nums copy. Let me make a copy, and then for I in range, say length s. So we are going to start from 1, right? Because for the power sum, the first term coincides with the original array. then basically Si is incremented by Si minus 1. So once we have this one, then we can prepare the finding the longest possible parameter. So as mentioned in this problem, we're going to return -1 if no such polygon formed. And then we are going to iterate. So for I in range 1 up to length S minus 1. So from 0 to this I, we have this many of edges. So then we can regard all of them as short sums. But the reason is due to this observation, right? So that's a sum, the length sum of certain set of edges is greater than A. So we can include all the smaller ones. So we just need to consider from the very beginning. So with the short sums, let's call it SI, right? Just to use this name to distinguish. You don't need to name it though. So what I'm going to do is I want to find this IDX. So I want to see after index I, in other words, starting from index I plus 1 and onwards, we see if we insert this short sums, then we see what's the index, right? Say bisect left. So what we are searching for is nums, and we want to search the insertion point for this short sums. So we start from I plus 1 and then ending at the length, right? So the reason is that if IDX is greater than I plus 1, right? It means that, so basically this means nums from I plus 1 up to IDX. So this piece contains elements that is strictly less than the short sums. With those elements, we can form polygons, right? So then in this case, the largest sum will be the max. So we max update the previous state, and then we use the short sum, then plus the longest edges possible, right? So this will be nums IDX minus 1, right? Because IDX is the insertion point, which is not counted, right? So this is the 1. Because this IDX minus 1 will be at least I plus 1, that is in the right of this index, right? So once you do this, basically for each index, up to each index, so we can find if we can form polygon and the largest polygon, including the first indices from 0 up to and include I, right? And then we are going to return the result. So this is the one solution format. Let's do a quick test. It passes the first one. Let's meet the major test case for among those 3 examples is this one, right? Let's test it. Yeah, it passes all the cases. So now let's do the generic case. Yeah, it passes all the generic cases, but for this bisect, it's not necessary. Let me write another solution, which is shorter, right? So actually, the second solution is still based on the observation that once we have the longest edge, so if we have a set of edges with sum larger than A, so once those can form polygon, we can add as many as shorter or equal edges with respect to this A, right? So this way means that we just need to consider all the cases. Let me first write the code. So let's do the sort, nums sort. And then what we're going to, let's see the answer equals -1 or result equals -1. Then we just use, let's see, short sums. So I'm going to set it to be 0. And then for y in nums. And then I want to see if this y can be used as a longest edge in a potential polygon. So the condition is this, y is less than the short sums. So notice that the short sums are starting from the very beginning and up to the current y, right? So this, but not included the y yet, right? In other words, you can just short sums is summation of length of the other edges, including this y, as polygon. So it means that we consider edges. So nums, so from 0 and including, let's see if this corresponding to I. So let's correspond to I minus 1, and then this nums I. So if this is the case, so we're going to update the answer to be y plus short sums. The reason that we don't need to do comparison is because as we move towards the right, actually this is larger, right? So the short sums is always larger. So this is the one uncheck. Otherwise, or if we cannot form polygons, we always do this. Short sums incremented by y. Now let me explain again. So this is the check. So in other words, if we can use the current y as the longest edge for a potential polygon, so no matter what, we are going to update the short sums. Actually, this is a partial sum, right? In this here, it's corresponding to this s. But you know, when we do the comparison, we don't need to do this. This actually saves a lot of time. So now we can return the answer state. So this is the second solution. So actually, let's first do a test and then make a comment. Yeah, it passes one case, and now let's look at the generic case. Yeah, it's much faster in principle. So here, so the two solutions are based both on those this very simple observation. So here, let's quickly analyze the temp complexity. So here, if for the first one, if you do sort, right? Sort, it's n logarithm n operation, right? So here for each I, so we do bisect. Essentially, you know, we do logarithm operations. So essentially, we have so for example, at index I, so we do a search. So the length will be log n minus 1. Let's see. Then for index 2, so we do, so here, more precisely, this has a length when I equals 1, and we start 1, right? The remaining is n minus 2, right? So anyway, so it's not very essential. Then for I equals 2, so then we are doing this n minus 3, and then we add log 1. Log 1 is 0, right? So this is roughly, you know, log m add up to log 1, right? Then if you want to do a more precise one, so this logarithm n up to logarithm 1 is nothing but logarithm n times n minus 1 times up to 2 times 1. In other words, this is logarithm n factorial. But if you know the Stirling formula, so let's see, we use Stirling formula. So you are going to get something like this. So n logarithm n, right? So you can more precisely something like this, but you can write the leading term. This is n logarithm n. So overall, the temp complexity is logarithm n. But here, if you count the temp complexity, so this is n logarithm n. And here, for this part, this for loop, this is the on, right? But you know, overall, the temp complexity is the same. But here, we need, in the first version, we need much more operations in the for loop, right? So that's the difference of the two solution formats. But I guess we shared the two formats of solutions. But in practice, so the second one is maybe better for a solution to this specific problem. But for practice purpose, we also explain version v1 just to practice binary search. So with that said, I guess that's it for the current problem. So thank you for watching.